Okay, welcome back to Pre-Calculus. Today we're going to start our new unit on limits, continuity and rational functions. And to start off with, I'd like you to take a moment and have a go at the do now. So let me give you a moment to do that right away. So hopefully you remember that for a linear function, the domain is simply all real numbers. But when we encounter these rational functions, that's a function that looks like a fraction, we've got to make sure that the denominator does not equal 0. And so the only way that the denominator can equal 0 is if x is equal to -2, or in the other case, -2 as well. Now, when we take a moment and we go ahead and actually simplify h of x, we see that there's a common factor in the numerator and the denominator. And so we end up with the function x plus 1, but we have to remember that that domain restriction, x cannot be equal to -2, still applies. So visually, when we graph these functions, what's the difference? Well, we know that if we're going to graph a function f of x equals x plus 1, it's simply a linear function with a y-intercept at 1 and an x-intercept at -1, and it's continuous, meaning its domain is all real numbers. With h of x, we agreed that there was this common factor in the numerator and the denominator. And once we simplify out that common factor, we end up with something that looks like a linear function, but there's this key domain restriction. X cannot be equal to -2. So how do we visually represent that? Well, the manner in which we do that is with something that we refer to as a hole. And the location of that hole, well, we know that the hole must be located at an x value of -2. How do we establish what the corresponding y-coordinate is for that discontinuity, for that hole? Well, the way that we do that is we use the equation y equals x plus 1, and we imagine what happens if we made x equal to -2. And you can see that that y-coordinate value is -1. And so the location of the hole is expressed as a coordinate of an x value of -2 and a y value of -1. But please remember that the function itself is not defined at that particular point. So, a couple of things that you need to probably remember from either Algebra 1 or Algebra 2, and the most important of which is the parent rational function. Now, all rational functions are related in some way to the function 1 over x. And I want to give you just a moment to quickly have a go at sketching that. So hopefully you remember a lot of that from last year, but for those of you that haven't encountered this before, maybe a table of values is useful for you. Please pay attention to this part here. We know that when x is equal to 0, f of 0 will be equal to 1 over 0, and that's undefined. The symbol for undefined is there. The domain for this function is that x cannot be equal to 0, and the range y is not equal to 0. We've got a vertical asymptote here, and the equation for that vertical asymptote is x equals 0. The horizontal asymptote is y equals 0. Those are useful reference points when we come to deal with transformations later. Just in case you've forgotten, the definition for an odd function is that f of -x is the same as -f of x. And you can see algebraically that that holds true for this function. It's decreasing on the domain -∞ through to 0 and 0 through to infinity. Notice, by the way, that the endpoints are not included. It's never constant, and it is discontinuous at x equals 0. And the type of discontinuity this time is different. It's a vertical asymptote. So as we look at these next two examples, I want you to think about the rules of transformations. Let me give you a moment to have a go, and then we'll talk through them together. So if we recall that the parent function is y equals 1 over x, we know that when we replace x with x minus 2, we're going to translate to the right 2 units. Similarly, if we take a function and simply subtract 3, we're going to translate down 3 units. And so perhaps the most useful characteristics on the parent function, a reminder, the parent function looks like this, are the vertical asymptote and the horizontal asymptote. We're going to use those as our reference points. So clearly, if we've moved to the right 2 units, our new vertical asymptote is going to be here. Remember that a vertical asymptote indicates where the function is undefined. If we plug in the value x equals 2 into the equation, the function is going to be undefined. Likewise, if we translate it down 3 units, then our new horizontal asymptote is going to be the line y equals -3. Please make sure when we ask you for equations of asymptotes that you're giving us equations. A useful reference point on the parent function is right here, the point 1, 1. And so we're going to use that same reference point here. And likewise, -1, -1 is a useful reference point on the parent function. So we'll use that same reference point here. On the upcoming quiz, we will ask you to go ahead and actually work out the exact value of the x and y intercepts, but that's not going to be our focus for today. And so the domain that we should have for this function is that x does not equal +2. The vertical asymptote is y equals -3. The horizontal asymptote is x equals 2. And the range is that y does not equal -3. Actually, notice I've got a mistake there for my domain. It should be that x does not equal 2. With the next example, you might want to rewrite the equation just so that it's easier for you to see the transformations that take place. So this time, we have a reflection. And this reflection here is a reflection, well, actually, to be fair, it can be perceived as a reflection over the x-axis or y-axis. I'm going to perceive it as a reflection over the x-axis. We've then translated 3 to the left, and we've translated up 2. So just as in the previous example, we're going to use the asymptotes as our reference points. And what we should be doing is piecing together a function that looks like this. And remember, on the quiz, you'll actually work out those x and y intercepts. As a last resort, you can always plug in values to see what's going on. But your domain should be x does not equal -3. Your vertical asymptote is going to be at x equals -3. Your range, y does not equal +2. And the horizontal asymptote is actually located at y equals 2. Let me just give you a quick moment to reinforce that skill set by writing the equations of the following 2 examples. So hopefully the first thing that you did is you identified the equation for the asymptotes. Then as a next step, what's really key is getting an idea of these reference points here. These allow us to see that in this case, there's been no vertical stretch and there's been no reflection. And so our equation is established up here. However, the transformations for the blue example, if we have a look at the asymptotes, we can see there's a translation to the left of 6, no vertical translation, but these reference points here help us to see that although there's been no vertical stretch, there has been a reflection. And so please make sure that you're paying attention to that negative sign in front of your function. So a large focus of today's class is how we examine what happens at these various different discontinuities. We've seen 2 different types today. One is a hole that we saw in the do now, and one is a vertical asymptote. What actually happens as we get to the function, as we get closer and closer to these particular discontinuities? Let me give you a moment to examine this for yourself by filling out the following table of values. Now, as we go through these examples, I'm hoping that you're going to feel that the filling out of tables of values is really a little bit tedious in a last resort. The emphasis really should be on a graphical approach. And we should really know what the function 1 over x minus 2 looks like. So here's the graph to the right-hand side. And if we're trying to examine what's going on at these discontinuities, one way in which we'll do it is we'll use the following sort of notation. So as x tends towards 2 from the left-hand side, one way we'll describe that is with a superscript minus. That means it's coming from the negative direction. The function itself, well, let's have a look. As we approach 2 from the left-hand side, what's the function doing? It's tending towards negative infinity. So the function tends towards negative infinity. And likewise, in red, as x tends towards 2 from the right-hand side, we're going to say from the positive direction, so we use a superscript plus. the function itself, well, let's have a look graphically. We can see that we're tending towards positive infinity. The function is tending towards positive infinity. So this notation is probably something that you're familiar with when you were describing end behavior last year. We're going to see if we can introduce a different type of notation that's preferential for calculus, and that's introducing the idea of limits. So let me give you a moment just to have a quick read through the methods and meanings, and we'll take a look at the following example. So while the graphical approach is preferential, there are going to be some functions that you aren't overly familiar with that you will encounter, and this is perhaps one of those. So take a moment, explore what's going on with the table of values, and then we can try and make some predictions about the types of discontinuity that we're seeing. Then go ahead and confirm that using your calculator. So you should have established a table of values that looks something like this. And perhaps at first glance, this limit notation is a little bit off-putting. So what we're going to do is we're going to explore this table on the left-hand side and use our old notation before we then consolidate the new notation of limits. So if we take a look at the information here, you can see that as the table progresses, we're getting closer and closer to the number 3. So as x tends towards the number 3, and remember we're approaching the number 3 from the left-hand side, so I'm going to put 3 minus here. What is the function itself doing? Well, the function itself is getting progressively bigger and bigger and bigger. So the function is tending towards infinity, and it's positive infinity. This might be how we would describe the function using last year's notation. As a limit, we'd express it in the following way. We'd say the limit of the function f of x as x tends towards the number 3 on the left-hand side is equal to positive infinity. That's how we go ahead and describe that limit. And actually, strictly speaking, infinity is undefined, so we would say the limit is itself undefined. The same is absolutely true here on the right-hand side, and so it's logical to suggest that given that we know there's a discontinuity at x equals 3, the function can't have 3 plugged in, it would have a 0 in the denominator, we predict that there's a vertical asymptote taking place at x equals 3. And when you graph it on your calculator, you can see that. Now, in this next example, we're again going to take a table approach to analyzing limits. By the end of the unit, quite frankly, you'll be able to graph that function comfortably. But let me give you a moment now to have a look at the tables and make some conclusions about limits and express what kind of discontinuity you think is taking place. So hopefully you correctly stated that the domain was x cannot be equal to plus or minus 2. That gives us a clue that there's discontinuities at those 2 locations, and we need to establish what type of discontinuities they are. You've had a look at the table of values and you've established that the limits coming from the left-hand side and the right-hand side of both of those discontinuities either shoot up to infinity or down to negative infinity. That's a major clue that we're dealing with a vertical asymptote at those 2 locations, and when you go ahead and you put that information into your graphing calculator, you're able to see that. Example 5 pulls together a variety of ideas, so let me give you a moment now to pause and have a go at this next one. So hopefully the first thing that you did is you went ahead and factored the denominator to identify where your discontinuities are located. You can see actually that we've got this common factor in the numerator and the denominator, and so that's a good indication that we've got something that we refer to as a whole. And actually this table of values on the right-hand side here really does indicate that. We can see that as x gets closer and closer to the number positive 1 from both sides, we're actually approaching a y value of 1 over 4, and that's really what these limits here indicate. Likewise, on the left-hand side, we can see that as x tends towards negative 3, we're either shooting up or down towards negative infinity, and that's a good indication that we've got a vertical asymptote at x equals negative 3. One thing to make sure that you are aware of is when it comes to graphing on your calculator is not going to be able to identify a whole, so watch out for that. So in your notes you have a quick summary of how to identify a whole or a vertical asymptote, and example 6 is an opportunity for you to have a quick bit of practice. Solutions are in Drive.